Okay, question number one. It's one of the chapter 2 question. In fact, maybe when you are solving the chapter, you solve this question. Two children are rolling automobile tires down a hill, and a hill is an inclined surface.
Yes.
Shazad claims that the tire will roll faster if he curls up in the tire center. And Laman claims that that will cause the tire to roll more slowly. Which child is correct? I will just open the chapter question just related to this one, then go on this solution. Okay, this question. So two children are rolling automobile tires down a hill. One child claims that their tire will roll faster, and if one of them curls up in the tire center, the other child claims that this will cause tires to roll more slowly. Which child is correct? I just added the names for the children. The question is this in the chapter review. Now it's an inclined surface, and we are going to use a model for this question when we did some problems about this. Maybe you remember when an object is released from rest from the top of an incline. So what is the speed of the object at the bottom of the incline? And if the speed is big at the bottom, so you can say that it's moving faster. But if the speed is slow at the bottom of the incline, you can say that it is slower. Now, and we know an equation how to get the speed, how to calculate the speed at the bottom of the incline, which is Heck equation. Remember this, 2gh divided by c plus 1 root 2gh divided by c plus 1. And this equation tells you that the speed at the bottom depends on two factors, in fact. G is constant for both cases, and height is constant for both cases. And you are going to roll the tires from the same height at the same place. And for both cases, you roll inside or do not curl inside. G and H does not make a difference, but C makes a difference. So how can we approach this question is this? Now I draw three figures in here. You see that. One of them is a tin hoop rolling, spinning about the center. Third one is a disc spinning about the center. And we know that tin hoop has the largest C, which tells you that it is slowest. And when we think about the disc, which is inside is completely full, it is a C which is 0.5 and 1/2. Then we can easily answer. So which, if we release these two figures from the same height, which one is faster? We can answer easily. It's the disc, not the tin hoop. But when you curl inside the tire, it's becoming not a disc, not a hoop, just between them. But C becomes less than 1. It decreases, gets smaller, but greater than 1/2. Yani when child curls inside the tire, the shape approaches to from the hoop to a disc, but not perfect disc. Yani full, but not perfectly full. Yeah, C gets smaller. Yani basically when the child curls inside the tire, C, yani the coefficient of the moment inertia gets smaller. And we know that if C gets smaller, of course, speed must get faster, greater. Yeah, when child curls inside this tire, because the coefficient shape changes, yes, shape changes. And by the time mass does not affect in this question, mass has no effect. As you see, there is no mass in the equation. Only because of there is a change in the shape, it can move faster or slower. How can we decide that? Because when it curls inside the tire, because shape gets closer to a disc than rather than a tin hoop, and C decreases. If C decreases, we expect we get faster. Yeah, that's why when they roll inside, or the child curls inside the tire will roll faster on an inclined plane. So Shazad claims that the tire will roll faster if he curls up in the tire center. So Shazad is right according to this explanation. Shazad, right. Levant claims that will cause tire to roll slower. No. When they curl, it gets faster. Which child is correct? Shazad is correct. Then let's continue with the second one. Two different masses are suspended from the each end of a simple beam. Simple beam is just a rod. To balance the beam, it must be suspended from the midpoint. It must be suspended from a point closer to greater mass. It must be suspended from a point closer to the smaller mass. It can be balanced at any arbitrary point, and any point you want. And remember, when we are talking about the center of gravity or center of mass, we said that if you support an object from its center of gravity or center of mass, object stays in equilibrium. And if an object is regularly, let's say, uniform, midpoint is the center of gravity. That's why when you support it from midpoint, you can balance it. But if the object is not uniform, just like a balance, because balance, yes, maybe it's a simple beam, but one side is heavier, the other side is lighter. So in this case, if this side is heavier, the center of gravity is going to be closer to heavier side. And we discussed this before when we are talking about center of mass, center of gravity. If this is the light side, this is heavy side, then center of gravity is going to be closer to heavier side. That's why you should support this balance from a point which is closer to greater mass. Yani it must be suspended from a point closer to center, it's a greater mass, then you can balance this simple beam. Clear?
Okay. Yes.
And next one, question number 3 is about a car parked on a bridge. A uniform bridge is located, supported by 2 pillars, located 3 meters from each end. A car is parked closer to the pillar on the left. Yes, this is here is the car, seen here. Which of the following is correct? Certainly correct. Certainly correct. Absolutely correct. Now, as you see, there are 4 forces acting on the bridge. 2 of them is reaction force by the pillars, Fn1 and Fn2. Other 2 forces are gravitational force and weight. One of them is the weight of the bridge. The other one is the weight of the car. And this bridge is balanced, which means net force acting on this bridge is going to be 0. Yani translational equilibrium. Sum of the force acting on the balance on the bridge must be equal to 0. Yani Fn2 is in positive y direction, minus Fg2 in negative y direction, minus Fg1 in negative y direction, plus Fn2 in positive y direction must be equal to 0. So these negatives transfer to the right side, so it's going to be like this: Fn1 plus Fn2, yani the forces which are in upward direction, is going to be equal Fg1 plus Fg2, which is the forces acting in the negative y direction downwards. So this is equal, and sum of Fn1 and Fn2 and Fg1 and F2 equal to each other. But when we see C, it says less. No, this is not correct. They must be equal. Yeah, the forces acting in positive y direction, some of these forces, magnitude of some of the magnitude of these forces in positive y direction, and some of the magnitude of the forces in negative y direction must be equal. And the next one is Fn2 is equal to Fn1, it says here. It is possible if there is no car. In this case, it's a uniform bridge. For a uniform object, we know center of mass or center of gravity is midpoint. And if you support it from midpoint, so you can balance it, which means that right side and left side force must be equal each other. Yeah. But in this bridge now, there is a car. What does it mean? Mass is closer. Which side is heavier in mass, left side or right side? Because car is closer to the left side, of course. Yeah, left side is heavier. This makes that Fn2 to be greater. Fn1, because car is closer to that pillar, it will act more force on the left pillar than the right pillar. In which side the car is closer, that pillar will apply, and more force will be applied on this pillar. Of course, this pillar will give a reaction with a greater force to the bridge. Yani A is correct. B and B, there is no such a rule. Just I wrote them randomly. There is no such a rule. Yani there is, we cannot prove this is correct. C, just we said that it must be equal. That's why it's not correct. And also, Fn2 and Fn1 can be equal if there is no car and just the bridge. That's why only correct answer in here is A. And next one is question number 4. Force times lever arm is equal to, it's the torque definition of torque. Everyone knows, I think, that force times lever arm is torque. And question number 5. 0.1 kilogram meter stick is supported at its 40 centimeter mark by a string attached to the ceiling. And 0.7 kilogram mass hangs vertically from the 50 centimeter mark. A mass is attached to somewhere on the meter stick to keep it horizontal. If the force applied by the string attaching this meter stick to the ceiling is 19.6 Newton, what is the value of the unknown force? This is also chapter 2 question. Let's go to the chapter 2 question. Yes, question number 36. A 0.1 kilogram meter stick is supported at its 40 centimeter mark. Yeah, question is exactly the same. Just I put the A part to the test bank as a chapter test. 0.8 kilogram mass is supported from 40 centimeter mark. Or you part 0.1 kilograms is supported from its 40 centimeter mark. Yes, this is the 40 centimeter mark. 0.1 kilogram meter stick. When it says meter stick, 1 meter long stick, you should understand that. Yani 100 centimeters. This 100 centimeters. I'm going to now say that this is 0. Here is 100. And its mass is 0.1 kilogram. That's why it's a uniform rod. You should draw it from midpoint. Midpoint is going to be, of course, 50 because total length is 100. Midpoint is 50. From 50, I draw the mass of the meter stick. And then it says it's attached to the ceiling by a string. Yes, this is the string attached to the ceiling. And 0.7 kilogram mass hangs vertically from 5 centimeter mark. From 5 centimeter, here is 0, here is 5. Another mass, which is 0.7 kilogram, is suspended. Then question says that if another mass, some mass attached to somewhere on meter stick to keep it horizontally and to provide the balance. If the force applied by the string attaching the meter stick to the ceiling is 19.6, yani we said we attached this meter stick to the ceiling, so this force in the string is tension, 19.6 Newton. Determine the value of the unknown mass. Yani a mass is unknown and attached from somewhere. How much is this mass? Question is this to balance this meter stick. Mass can be easily calculated because there are one unknown mass, because each mass causes a force. And there are, in this case, just one unknown mass and just one unknown force. M1 is known, M2 is known, Ft is known. This is only unknown. And maybe you remember we said that if there is only one unknown in a problem, we can, or equilibrium problem, we can use translational equilibrium. Yani net force acting on the beam or meter stick must be equal to 0. So I'm going to apply the translational equilibrium to calculate this and calculate the value of the unknown mass. Sum of the force acting on this meter stick must be equal to 0. But when I check the question, I see that M1 is mass, M2 is mass, but tension is force, yani Newton. I can go this way. I can calculate the equivalent force, gravitational force M1 and gravitational force M2. Yeah, we can do that because by using M1G. And after that, we can calculate how much gravitational force is applied by this unknown mass. Then I can calculate M by using Fg is equal to M times G. Or maybe scientifically not a good way, but as a result, it doesn't change, and much easier one. I say that instead of changing the masses to the force, you know, two masses to the force, and again back to the mass, let's change the force to mass, yani tension. Let me change this tension to the mass. How? You know, F is equal to M times G. So if I divide this force by 9.81, I can calculate equivalent mass of this force. When I do it in here, it's 2 kilogram. Yani this is a force which is equal to the weight of 2 kilogram object. Yani upward direction, I am going to say that there are a force acting which is equal to 2 kilogram object. Downward direction, I have a force acting downward equal to weight of 0.7 kilogram object and the weight of 0.1 kilogram object. Then calculate the mass of this object. So apply translation equivalent, but only using the mass instead of force. Sum of the mass, yani acting on the meter stick is going to be 0. So as I see 0.7 in negative y direction, I did in negative 0.7. 19.6 equivalent to a mass which is 2 kilogram. I calculated in here. So it is in positive y direction. That's why I am going to write it positive 2. 0.1 is in negative y direction. I am going to write in negative 0.1. And unknown mass, I will say mx calculated in negative y direction. I read negative mx. Sum of them is going to be equal to 0. Mathematically, if you continue from this on this, you will find this unknown mass is equal to 1.2 kilogram. And then this question is completely about that. And I didn't even change the numbers. So when you apply all this, you will get the result as maybe I changed the number because here is we have 1.2. Yeah, it was 1.2, correct? Yeah, 1.2. So B is the correct answer. This question also has the second part, which I didn't put the test bank, but it also asks you the point where the mass attached to the skin. Yani what is this? From how many centimeter you have to, you have to suspend this 1.2 kilogram mass. Yani what is that point? How many centimeter? Of course, when you are calculating the length, you have to use rotational equilibrium. Yani distances, if you want to calculate a distance about the equilibrium problem, we cannot use translational equilibrium. We have to use rotational equilibrium. So part B, I applied rotational equilibrium. How? I know all the forces now, all the masses and forces. Upward direction, there is a force which is equal to 2 kilogram mass. Downward direction, two of them given in the question, one of them I calculated. Just like applying the rotational equilibrium, how we did it by the force. But I'm going to do with mass, only mass. You can convert them force again, but it's going to be a very long solution if you do like this. Mathematically, if all are mass, it's okay. Or if all are force, it's okay. So then I am not going to convert all these masses to the forces. I will continue just the masses. Yeah, and each mass produces a torque. Mathematically, I am going to do that. But of course, you should choose an axis of rotation. And remember, I said that you can choose any point you want. Best way is to choose the position of an unknown force. But in here, there is no unknown force. All are known. So then you are going to choose one of them. Which one you prefer? It's up to you. So I choose this point. If you want, you can choose that point as well. And now I will continue according to the point I choose. Yani position of the tension force, yani 2 kilogram mass, I indicated the axis of rotation. I know that that point is 4 centimeters. According to this point, M1 causes a counterclockwise rotation. That's why it produces a positive torque. M2 causes, according to this point, a clockwise rotation, negative torque. Also, this unknown mass, which we calculated, produce a clockwise rotation, negative. One by one, I will calculate the torque of each force. But again, I will use centimeter because I will find result centimeter. Yani if the result you are going to find centimeter, you can use centimeter in calculations, in this calculation. Yani I use the mass in kilogram and distance from mass to the axis of rotation. From 5 to 40. From 5 to 40, how much is the distance? 40 minus 5, yani 35. So it is 35. Then I calculated torque produced by this 0.7 kilogram mass, which is 24.5 kilogram centimeter. Then I calculated torque of M2. It is negative because it causes a clockwise rotation. 0.1 is the mass. And what is distance from 50 to 40 centimeters? It is 10, subtraction of them, 10. Then I calculated torque of M2. And then I calculated torque of unknown mass, which we calculate in the first part. Again, it causes clockwise rotation, so negative. Mass is 1.2. Distance is what? That's the point. I will calculate x. I don't know how much is x. But I know that if I subtract this x, pardon, for this 40 from x, I can calculate that distance. Yani here, I need this distance. Let me show this. This is the distance for 1.2 kilogram. I know from here to there, it is 40 centimeters. From here to there, it is x. I don't know how I will find it. But if I subtract this 40 from x, I will calculate distance for 1.2 meter, 1.2 kilogram force. That's why I will write in here x minus 40. Then I will find x. Add all the torques. Net torque is going to be 0. Add them all. 24.5. Negative 1. Then negative 1.2 times x minus 40. Sum of them is going to be 0. Then transfer this to the right side. And after that, go on with mathematics. You will find result as x 59.6 centimeter. Yani you should suspend this mass from this point, which is 59.6 centimeter. Then I will continue with 6. If there is a net torque acting on an object, of course, if there's a net torque, then I times alpha. Remember equation. If this is known as Newton's second law for rotation. If there's a net torque, there's absolute acceleration. If there's an acceleration, angular speed must change. Correct. Angular momentum stays constant. Impossible. We know that it's the only condition how we change the angular momentum. If there's a net torque acting on an object, angular momentum changes. Yani cannot stay constant. See, moment of inertia increases. Moment of inertia just depends on the shape or mass or axis of rotation. So net torque cannot make a change in moment of inertia. So this is also not correct. All of the above is correct. No, just A is the correct answer in here. And question number 7. An ice skater is spinning on ice. Then he brings his arm invert. So for ice skater, this is about the conservation of angular momentum. It's absolutely because ice skater on the ice friction force is almost 0. That's why net torque is equal to 0. If net torque is equal to 0, the angular momentum is conserved. So first choice is not correct because angular momentum is conserved on ice. If angular momentum is conserved, now which we say that L is equal to I times omega, but the ice skater brings his arms inward, which means making the arms closer to extra rotation. Then if mass gets extra rotation, moment of inertia decreases. To keep the because angular momentum is constant, angular speed must increase. So let me stop this. Yes, as I said, angular momentum increase not correct because ice on the ice net torque 0. That's why angular momentum constant. According to constant angular momentum, I times omega, because when his arms bring invert, I decreases. Decreasing i's cause an increase omega because L stays constant. Angular speed increases. It says B says angular speed decreases. Not correct. Rotational kinetic energy increases. Yes, rotational kinetic energy increases. You can write the equation because rotational kinetic energy equations 1 over 2 I omega squared. Omega increases. Even how much, by what factor I decreases, omega increases by the same factor. If moment of inertia, say that decreases by 2, angular speed increases by 2, but angular speed has a square. That's why the square of 2 is 4. The moment inertia decreases by 2, 4 over 2, result is 2. Yani this is also a rule. You should know that about ice skater questions. When the ice skater open his arm or close his arm, by what factor angular speed changes? Rotational kinetic energy changes by the same factor. Yani you can learn it without calculating. Yani for example, say that in this question, moment inertia decreased by half, angular speed doubled. Rotational kinetic energy also doubled. If moment inertia decreased by 3, angular speed increased by 3, rotational kinetic energy also increased by 3. Yani the change in the angular speeds, whatever this change is, rotational kinetic energy will have the same change. So we know that angular speed increases, rotational kinetic energy also increases. A moment inertia increases? No. When you take the arms inwards, you are making the distribution of mass get closer to the axis of rotation. That's why moment inertia decreases. This must be decreases. Question number 8. If Earth were a spherical shell rather than a solid sphere of the same mass, radius, how would one day of the Earth change? One day, a day is determined by the speed. Yani if Earth start to rotate faster, days are going to be shorter. If Earth starts to rotate slower, days are going to be, in this case, longer. Yani question is in fact asking you, if Earth were a spherical shell rather than a solid sphere, will its angular speed increase or decrease? Okay, now let's check it. L is equal to I times omega. If initially it's now right now we know it's solid sphere, its coefficient of moment inertia 2 over 3 mr squared. But if it were a spherical shell, it would be 2 over 5. If it's a spherical shell, it becomes 2 over 3. A spherical shell has a greater moment inertia. Yani if Earth were not a solid sphere spherical shell, moment inertia of the Earth will increase. But angular momentum, same, because the question is not talking about some external torque acts on the Earth. If moment inertia increases, angular speed must decrease. If angular speed decreases, which tells you that Earth starts rotating slower. And if it is rotating slower, it completes one rotation in a longer time. Yani one day of the Earth is going to be longer. It would be a longer day. And question number 9 is about conservation of angular momentum again. A child on a merry-go-round moves from outer edge to near the axis. Yani get closer to the center. Yani if the child starts to move to the center, which means distribution of mass gets closer to the axis of rotation, moment inertia decreases. To keep angular momentum constant, so angular speed must increase. So moment inertia decreases. This is correct because child is getting closer to axis of rotation. Angular speed increases, also correct. Rotational kinetic energy increase is also correct. Remember, I told you that in the previous question. In the conservation of angular momentum problems like merry-go-round or ice skater, whatever the angular speed change, how angular speed changes increase, rotational kinetic energy also increases. If angular speed decreases, rotational kinetic energy also decreases. Even they change by the same factor. Yeah, and this is also correct, both increase. So D is the correct answer in here. Question number 10 is one of the section question. Also read it at the end of the section 3 of chapter 2. This one. A bicycle designer recently modified a bicycle by adding cylindrical weights to the spokes of the wheel, moment inertia of the wheel. Remember, we said that moment inertia depends on three things: mass, shape, and axis of rotation. In here, you are adding mass. If mass is added, it doesn't matter where you add mass. Moment inertia always increases. So the answer is going to be increase. There is no other way. Because you are adding mass to the system from outside, increasing mass always causes an increase in the moment of inertia. Question number 11. A spinning ice skater decreases moment inertia of his body. This is again conservation of angular momentum. Decreases the moment inertia of the body in how? By moving his arms inwards. So, by how does his rotational kinetic energy change? Right now, I explained them to you. If moment of inertia is halved, angular speed is doubled, because to keep angular momentum constant, and by what factor omega changes? Rotational kinetic energy changes with the same factor. In here, angular speed increases by 2. So rotational kinetic energy also increases by a factor of 2. You don't need to make any calculation. Just answer in these types of problem this way. But don't forget, this is about questions about conservation of angular momentum, not other questions. Question number 13. It's about angular momentum. Calculate the angular momentum of Earth that arises from its spinning motion on its own axis. Spinning about its own axis, you are going to treat this sphere as an extended object, and it's spin about diameter. Its moment of inertia equation is going to be for this planet 2/5 mr squared. So we know m is given, we know rr is given, so we can easily calculate moment of inertia. But to calculate angular momentum, we also need to know what is omega of this rotation, because of the rotation of the Earth. First, we should get omega. We know that omega is equal to delta theta over delta t. We studied in chapter 1, section 1. Earth completes one rotation about its own axis in 24 hours, one day, yani. 24 hours must be converted to second by multiplying 60. You convert it to minute by multiplying 60. You convert it to second. Yani one day is equal to 24 times 60 times 60 seconds. And one rotation, and one day is one rotation about its axis, and one rotation, angular displacement is 6.28. So by this way, we will first calculate how much is the angular speed. This is angular speed. To calculate omega, I need to multiply omega and I. So just let's multiply. I is 2/5. M is 5.97 times 10 to the power of 14 times radius is given as 6.4 times 10 to the power of 6, but we should square the radius. Multiplied by omega, right now you calculate it, 7.26 times 10 to the power of -5. When you calculate them all, you will get the correct answer. Spinning motion, because of the spinning motion of the Earth, we have days. But next question is about orbital motion.
So it's about year?
It's about year, yes. In the first one, you are going to treat the Earth as a solid sphere, because it's a solid sphere about its diameter. When it produces one day. But second one, orbital motion is about Earth, about Sun. So when Earth is or in orbital motion, you should treat the Earth as a point mass because it's in circular motion. Yani moment of inertia equation is going to be mr squared in here. Students do mistake in this question this way. Yani they say that, oh, Earth is sphere. Okay, sphere, but what kind of motion is it? Is it rotational motion or circular motion? About sun, it's circular. That's why you should treat the Earth as a point mass. Then equation for moment inertia of the point mass about an axis mr squared. That was the difference between these two questions. The rest is, what about omega? Also, you should calculate omega. It's 1 year this time. For one rotation revolution, angular displacement 6.28. For one revolution takes 365 days this time, not 1 day. Days to the hour multiplied by 24. Hour to minute multiplied by 60. Our minute to second multiplied by 60. By this way, you will first calculate angular speed of Earth around the sun. After that, you will multiply by mr squared, and you will find how much is the angular momentum. Which object has the moment inertia of mr squared? We know it. It's the circular motion or thinner about symmetry axis. Upon is about an axis. Yani it's going to be by the shape, moment inertia shape, you can see that. Thinner about diameter is 1 over 2 mr squared. Thinner about symmetry axis is mr squared. Point is about an axis, which is the circular motion, also mr squared. Yani this is the correct answer. The bodies that move in a circular path may never be in translational equilibrium, in complete equilibrium, in rotational equilibrium, both A and B. If an object is moving in a circular path, there must be a resultant force acting on this object, which is called centripetal force towards the center. There is a resultant force. Yani net force is not equal to 0. If net force is not equal to 0, so translational equilibrium is not possible. If translational equilibrium is not possible, complete equilibrium also not possible, because complete equilibrium requires both rotational and translational equilibrium. How rotational equilibrium could be possible? Yes, if an object is moving in this circular path with constant tangential speed, yani v constant, omega also constant. If omega constant, alpha 0. Yani possible. Rotational equilibrium can be possible, but translational equilibrium impossible for a circular motion. There's always a force acting on an object to cause it to follow circular path. Yani A and B is not possible, but C could be possible if you keep object in the circular path with constant tangential speed, with constant angular speed. And question number 7. This question may be close to the previous one. An object rotates with a constant angular speed. This time, omega constant. Omega is constant in this question. Omega constant. So if omega constant, we can say alpha 0. If alpha 0, according to the Newton's second law for rotational motion, net torque 0. Net torque 0. No net torque acts on the object. No net torque, correct. That's correct. No net force acts on the object. How do we know it? Maybe there are two forces which produces oppositely directed torques. Net torque can be 0. Yani we cannot be sure about this. Yani about B, we are not sure. Object is in rotational equilibrium. This is correct. Why? Because alpha 0. If angular acceleration is 0, rotational equilibrium. If linear acceleration is 0, translational equilibrium. Alpha 0 in here, we can say that C is also correct. Yani A is correct, C is correct. Yani D, both A and C are correct in this question. The next one is question number 18. An object is at rest. you can be certain that if an object is at rest, equilibrium.
Omega is 0.
Yeah, both equilibrium exists. If an object is at rest, you can say that translational equilibrium exists, rotational equilibrium exists. Both of them exist. Yani net torque zero, absolutely correct. Net force zero, absolutely correct. No external torques X on the object. Maybe there is. One of them clockwise, the other one is counterclockwise. We cannot be sure about A. We cannot be sure about A. But we are sure about B. Why? If an object is at rest, alpha zero. If alpha zero, net torque zero. If an object is at rest, linear acceleration is zero. If linear acceleration is zero, net force zero. So no net force, no net torque, correct. So D is correct answer. About A, we are not sure because, as I said, there can be external torques, but they can cancel one another. Question number 19. A simple pendulum, this is the question in the book. Yani, it asks you calculate the magnitude of the torque due to the force in the string. Remember, when I was solving this problem, I said that tension force never produces a torque. Why? Because tension force always acts along the string. For a pendulum, as pendulum swings, so let me draw a pendulum. So tension force, this is Fg. Tension force extension always passes through the axis of rotation. If a force extension passes through the axis of rotation, its torque is always zero. That's why tension force can never produce a torque on a simple pendulum, zero. And you don't need to calculate anything in here. Now, question number 20. A bucket filled with water is attached to a rope wound around the cylinder with a radius of 0.05 meter at the top of the wheel. The weight of the water and the bucket produces a torque of 11 Newton meter on the bucket. What is the total mass of the bucket? There's a picture given. In fact, this question is also chapter 2 question. I draw diagram in this chapter question very clearly, much better than this. But this diagram normally not given in the book, so we have to learn how to solve this problem. And even they don't change the questions, then you will learn how to solve this, and you will do solution after that. So this is the bucket. Of course, it has some mass, and because it has some mass, it acts some force, gravitational force, and this force is transferred by the rope on the cylinder. You see the cylinder of this. What can it cause to lift the water from the wheel? So this force acts tangent to the surface of the cylinder downward like this. Acts tangent. Why? Because rope is tangent to the surface of the cylinder. If a force acts tangent, now I'm going to draw a shape when you look at from this side. Here is the cylinder's this side, this section. Here is the axis of rotation. The force will be acting on the cylinder's surface downward, tangent to the cylinder with Fg. I draw this in such a way that we are looking from the rear side. And radius of the cylinder is going to be in here, the distance for the force. It's given in the question, 0.05 meters. And of course, this force will produce a torque about this point, and we know how to calculate this. And I know that tangent line is always perpendicular to the circle or the cylinder surface. Then torque produced by Fg is going to be Fg times distance times sine theta. Torque is 11 Newton. Fg, what is mass? I will find mass, but before finding mass, I should find Fg. Distance is the radius of the cylinder, 0.05. Angle is between the radius and the tangent line is 90. Sine 90 is 1. So Fg is going to be 11 divided by 0.05, which is going to be 220 Newton, but it's Newton. But we need to calculate the mass. You have to divide this by 9.8. 81, because we know that Fg is equal to m times G. Mass is going to be Fg divided by G. 220 divided by 9.81. 22, how much?
22.42.
Yani almost 23.
True.
So B is the correct answer. And question number 21. Two spheres have different diameters, but the same moment of inertia. It is certain that, again, two spheres, they have same moment of inertia, but different diameters. If diameters are different, radius are different. So I will write the equation 2/5. I am not sure about the mass. I will write m1 for the first sphere, but they have different diameters. They have different radius. Yani R1 for the first one, but their moment inertia same. Yani first sphere's moment inertia and second sphere's moment inertia equal. Question tells you that. I'm not sure about their masses. I will write M2. And also I'm absolutely know that their radius and diameters are different. This is 2/5 simplify. So M1 times R1 squared and M2 times R2 squared are equal. But these are different. Yani if R1s are different, radius are different, to make them equal, M's must be different as well. Yani this is impossible. R1 and R2 and different, but you multiply both sides with the same number, they can be equal. No. If R1 and R2 are different, if you multiply them by the same number, they are different again. But to make them same, you should multiply them with different numbers. That's why M1 and M2 must be different to make moment inertia equal. Yani if R1 and R2 is different, absolutely question says they are different. M1 and M2 must be different to make them equal. To make them equal. You can give numbers. For example, say that R1 is 3. R2 is 5. So they are different numbers. If I multiply by them the same number, same mass, one of them is 6, the other one is 10. They cannot be equal. But if I multiply them like this, 3, for example, 3 and 5, 15.
And 5 is good.
Yeah, as you see now, I multiply them with different numbers. They make them equal. Yani if R1 and R2 different, absolutely M1 and M2 must be different. Then let's continue with this. The spheres have the same mass. Impossible. The spheres have different mass. Must be. One sphere has twice. And maybe yes, maybe not. We are not sure about this because we don't know what is the relation between the radius. Maybe one of them is twice or half or 3 times. So we cannot be sure about this. One sphere has 1/3 of the mass. We are not sure about this, but we only know that their masses are different. This is what we know. B is correct answer in here. Question number 22. It's about opening a can. A 21 centimeter screwdriver is used to pry open a can of paint. If the axis of rotation is 2 centimeters from the end of the screwdriver blade, and 64 Newton is exerted at the end of the screwdriver handle, how much is the torque produced by the screwdriver? Now, this is this picture how we open the can of a paint. I will draw it a little big. This is the can. And there's a lid, something like this. If you want to open this lid, you should use a screwdriver, but screwdriver's blade must be put just under this lid. Because when you are applying a force in this end with your hand, about this point, which is the axis of rotation, the screwdriver will rotate and push the lid above, upward direction by a force. But if the screwdriver is pushing this lid upward direction, lid gives reaction, this screwdriver blade downward direction. There are action-reaction forces equal in magnitude, opposite direction. And if you calculate this force, that is the same. And this force is the same of that one. So question tells you that this Screwdriver is 21 centimeter. And total length is 21. Let me show it. From the blade until the hand that you hold, 21 centimeter. And extra rotation is 2 centimeter from the blade. Blade is here. That length is 2 centimeter. Yani from extra rotation until the force applied on the lid and the blade, this distance is 2. In this case, that other side is going to be 21 minus 2, yani 19 centimeter. So then question is asking you, what is the torque produced by 64 Newton force exerted at the end the handle? Handle is in here. So I know force, I know distances, which is 90 centimeters, angle is 90. Calculate torque, Fd sine theta, F64. Distance is 21 minus 2, because I know that total length is not the distance for the force. This is the forces from handle until axis of rotation, yani H. So it is 90 centimeter, 0.19. Angle is 90, sine 90 is 1. Just multiply and find the torque. I think answer is going to be 12.2, I think. And question number 23. For which of the following objects during rolling, it is total kinetic energy is twice of the rotational kinetic energy. Total kinetic energy twice of rotational. And rotational kinetic energy, if you say 1 joule, total is going to be twice, yani 2 joule. To get the which shape is it, I'm going to use this Hayek equation. Remember, maybe if we divide rotational kinetic energy by total kinetic energy, we got C equation. Because C tells us what is the shape. C divided by C plus 1 for a rolling object. Yeah. If we get how much is the C, then we can predict which shape it is. Rotational is 1 joule. We said 1. Total is twice, yani 2, equals C divided by C plus 1. Cross product, C plus 1 is going to be 2C. Transfer this C to the right side, it becomes C is equal to 1. So which shape in here has C1?
Tin hoop.
It's the tin hoop, yes. Ring. Ring has the C1, that's why answer is D. Question number 24 is the arm of a crane at the construction site is 50 meters long. It makes an angle of 40 degrees with the horizontal. So this is the crane handle, crane arm, sorry. And crane arm is making an angle of 40 degrees with the horizontal. And from the top of the crane, you suspend a load, some load, and then you are lifting it. Assume the amount of torque the load produces around the base of the crane, yani here, about this point, extra rotation. Torque is 6,342 Newton meters. What is the maximum load? Yani calculate Fg. Load means gravitational force. When the handle is at an angle of 30 degrees with 40 degrees with the horizontal. Okay, if this is 40, this is 90 degrees, we know that, because horizontal and vertical angle between them is 90. If this is 30, that must be 50. Why did I get this angle? Because I need to know the angle between the force line and distance line to calculate the torque. I said to you several times. This is distance line, this is the force line. I need angle between them. And I know the arm, and distance is equal to 15 meters. Question in the question is given 15 meters. Only I have to use the torque equation, which is torque is equal to Ft sine theta. Torque is going to be, it's given, torque is given 6,342. Force is the question, how much is the load? Distance is 15, sine 50. I will calculate force. So transfer this to the left side and divide that. F is equal to 6,342. 15 times sine 50, sine 50. It's going to be 552 Newton. Yani B is the correct answer. And question number 25. A 350 kilogram merry-go-round in the shape of a horizontal disc. This is capital M with a radius of 1.5 meter. Radius is set in motion by wrapping a rope around the rim of the disc and pulling the rope. This is also chapter 2 question. I will draw the shape in here. Merry-go-round is a disc and there is a rope wrapped around the merry-go-round and you will pull it by a force. Of course, this force produces some torque about this merry-go-round and it will cause it to start rotating. A constant magnitude of the force applied tangentially, as you see as I draw, it brings the merry-go-round from rest to an angular speed of 314 radian per second in 2 seconds. How much is the force? Calculate the force. I'm going to use the torque equation to calculate the force. Torque is equal to F d sine theta, sine 91. Distance is the radius, which is given as 1.5 meter. I can calculate force if I know the torque. Can I calculate the torque? Yes, I can, because I know that it accelerates from 0 to 3.14 radian per second in 2 seconds. I can first calculate alpha, which is omega final minus omega initial divided by delta t. Final is 3.14, initial is 0, divided by delta t is 2 seconds. Alpha is going to be, I think, 3.14 divided by 2,
57.
1.57 radian per second square. So I know alpha, then I'm going to use Newton's second law for rotational motion to calculate the torque, I times alpha. I use it's a disk, 1/2. M is 350, R is 1.5 squared multiplied by 1.57. So this is the torque produced by this force. How much torque is produced? Let's calculate that. Now let's write torque in here. 1,236 is the torque. F is the question. Distance is 1.5. Sine 90 is 1, no need to write. Divide this number by 1.5. Question number 26, a cable passes over a pulley of the radius 0.5 meters. The force in the cable on one side is 110. The force on the cable on the other side is 100. Calculate angular acceleration of the pulley if its moment inertia is 0.75. Okay, there is a cable is just like a disc. One side you apply 110 Newton, other side you apply 100 Newton. So calculate angular acceleration, but angular acceleration can be calculated if you calculate torque first. Easy to calculate because it's a disc. Cable is just like a disc. So it's more, even the moment inertia is given, you don't need to calculate it. It's given the question. So to calculate alpha, first I have to find how much is the net torque. One force produces positive torque, the other one negative. We don't, because it's the magnitude. We don't need to care which one is clockwise, which one is counterclockwise. It's not given in the question is even. So just do it like this. 110 Newton, 110 Newton, of course, must produce more torque than 100 Newton because their distance are the radius, they are equal. Yani 110 times radius minus 100 times radius is going to be the torque. So take the radius parenthesis, it becomes 110 minus 100 times R. Yani net both force produces opposite directed torque. You should subtract them. Then multiply them by common distance. Both have the common distance from left and right, radius. So 10 times radius is going to be 0.5. This is the torque produced by, net torque produced by these forces. Then it's going to be I times alpha. I is also given, it's 0.75. So divide 10 times 0.5 by 0.75, you will find the answer. So this is this, 726. Okay, two forces equal in magnitude but opposite in direction act at the same point on an object. So two forces equal in magnitude but opposite in direction acts on the same point on an object. The object is in translational equilibrium. So now let me draw the cases. So say that this is an object. On this object, two forces X at the same point. Right here, say that point. But these forces are going to be in opposite direction, like that. And they will have equal magnitudes, say that 10 Newton and 10 Newton. So the object is in translational equilibrium, correct, because net force acting on the object is going to be zero. One of them is in positive y. The other one is in negative y, or positive x, negative x. So two forces opposite in direction, equal in magnitude. Sum of them is equal to zero. So because sum of the force acting on the object is equal to zero, so it's condition for translational equilibrium. What about rotational equilibrium? If you choose an axis for calculating torque, for example, here or here, it doesn't matter, or any axis, distance from each force is going to be the same. Distance from force to the axis of rotation is going to be the same. Yani each force produces equal magnitude of the torque, but one of them produces a clockwise torque, the other one produces counterclockwise torque. One of them positive, the other negative, the other one positive. So equal torques, but opposite in direction, which means net torque is also zero. If net torque is zero, object is in rotational equilibrium as well. So if an object is in rotational equilibrium and also translational equilibrium, object is going to be in complete equilibrium. Then question number 28. There are three objects: cylinder, solid sphere, spherical shell, with equal radii and equal masses. All gain equal angular accelerations by applying different magnitude of torques. Which shape requires the most torque? So torque depends on moment of inertia and also multiplied by alpha. So when we multiply torque, moment of inertia, and angular acceleration, we calculate the torque. But the question says you that all gain equal angular accelerations. Yani alphas are equal for both all shapes. Then if which one require most torque, yani to make if one of them requires most torque, its moment of inertia must be the greatest. Greatest moment of inertia of the shape requires the most torque. And in this given, the spherical shell has the most greatest, yes, the greatest moment of inertia, 2/3. So that's why C is going to be the correct answer in here. Mathematically, it's so clear because alpha question says that they have equal angular accelerations, and alphas are the same for all. Then you will check that. The one with greater moment inertia requires more torque. The one with the greatest moment inertia requires most torque. So spherical shell has the greatest moment inertia in here, because 2/3, which is 0.66. This is 0.4. This is 0.5. So that's why spherical shell requires the most torque to accelerate at the same acceleration with the others. Then question number 29. Angular momentum is conserved for an object. Angular momentum is conserved for an object. So let's quickly remember condition. So in physics, every conservation law has a condition, remember? Angular momentum conserved if net torque acting on the object is equal to zero. So let's remember this first, and after that, let's continue. So A, the net external torque produced on the object is zero. Yes, this is the condition for angular momentum's conservation. B, total mechanical energy of the object is conserved. We don't have such a condition for angular momentum conservation. Moment inertia stays the same. Why? Why should stay the same? Angular speed stays the same? No. And the only condition for angular momentum to be conserved is net torque acting on the object must be equal to zero. Yani correct choice is A. Question number 30. A cylinder rolls along a horizontal surface at a constant linear speed without slipping. What is the ratio of the translational kinetic energy of the cylinder to total kinetic energy? In fact, we have the hack rule for this. In the classroom, we did this. Kinetic energy translational, pardon, kinetic energy rotational divided by kinetic energy total equals to C divided by C plus 1. Do you remember this?
Yes.
So we can produce more hack rules, but more hack rules causes more confusion. Sometimes you get confused. This is okay, sort of all the problems. But this one calculates rotational kinetic energy divided by total. But question is asking you ratio of translational kinetic energy to the total kinetic energy. First calculate this, then continue the problem. So I know it's a cylinder. Cylinder C is 1 over 2. 1 over 2 mr squared. So I will write instead of C, 1 over 2 divided by 1 over 2 plus 1. So numerator is 1 over 2. Denominator is going to be 3 over 2 when we add that. Flip it and then multiply. Kinetic energy rotational divided by kinetic energy total is going to be 1 over 2 multiplied by 2 over 3. These twos will simplify 1 over 3. This equation tells you that if rotational kinetic energy is 1 joule, total is 3. What about translational? So difference between them, because we know that total kinetic energy, which is in denominator, is sum of rotational kinetic energy plus translational kinetic energy. If rotational kinetic energy is 1 joule, if the total is 3 joule, kinetic energy translational must be how much? 3 minus 1, which is 2.
2.
So we got translation kinetic energy. Then you are going to divide it by total. Total, how much we calculated? 3. So answer is going to be 2 over 3.
3.
This is the answer. A thin spherical shell, which is called halosphere, rolls along a horizontal smooth surface at a constant linear speed without slipping. The ratio of the rotational kinetic energy about center to translational kinetic energy. In fact, the previous one and this one is same way. We will do the same method. We know that kinetic energy rotational divided by kinetic energy total, just one hack I am going to use for all problems. Then I will use a little mathematics. So it is a thin spherical shell. So I know that this is equal to C divided by C plus 1. Thin spherical shell has a C which is 2 over 3 mr squared. So 2 over 3 is the C. Let's insert C, 2 over 3 divided by bracket 2 over 3 plus 1. So which is going to be 2 over 3 is the numerator. Denominator is going to be 3 times 1, 3 plus 2, 5, 5 over 3. When we flip this 5 over 3, result is going to be 2 over 3 times 3 over 5. And result is going to be 2 over 5. The kinetic energy rotational divided by kinetic energy total is 2 over 5. Yani if rotational kinetic energy is 2 joule, total is going to be 5, according to this. But the ratio is not this, which is asked in the question. What is asked in the question? Ratio of rotational kinetic energy to translational. Yani kinetic energy rotational divided by kinetic energy translational is asked. Okay. Rotational kinetic energy, I know, 2. Translational must be 5 minus 2 because total is 5. Total is sum of rotational plus translational. At rotational is 2. How much I have to add to 2 to get 5? Translational is 3 in this case, correct? So
Yes.
translation is going to be total 5 minus rotational 2. So it's going to be 2 over 3. Yani this is the correct answer. And question number 32. The combination of an applied force and a frictional force produces a constant torque, 24 Newton meter, on wheel rotating about a fixed axis. This is torque. Torque net, in fact, because this torque is produced by two forces, applied force and also friction force. It's a net torque. Net torque, 24. The applied force acts for 5 seconds, which means friction force cannot be removed. Yani friction force always exists. You cannot remove it in real life. But applied force acts for 5 seconds means this net torque, yani addition of the frictional force, torque of the frictional force, torque of the applied force, yani net torque acts for 5 seconds. And during this time interval, the angular speed of the wheel increased from 0 to 15. What is the moment of inertia of the wheel? So there's only one way to calculate the moment inertia. Torque is equal to I times alpha. So torque is given for 5 seconds. How much torque, net torque acts on it? It's given. Alpha can be calculated because angular speed change is given. We know alpha is, from definition of the average angular speed, omega final minus omega initial divided by delta t. So omega final is 15. Initial is 0. In 5 seconds this happens. 15 divided by 5, alpha is going to be 3 radian per second square. Now I can use the given information from the question. Net torque is 24. I is the question, multiplied by alpha 3. Divide by 3, divide by 3. 24 divided by 3, which is 8. The moment inertia of this wheel is 8 kilogram meter squared. 33. A mass is attached to a cord that is wrapped around a wheel with a radius of 10 centimeters as shown in the figure. The acceleration of the mass down the frictionless incline is 2.5. I wrote 2.5 in the question, so according to which one I wrote, I don't know. I made a change in the acceleration, but I forgot to change on the picture, on the figure. Figure written 2, and the question written 2.5. Okay, we will do one of them. Which one is correct? I am not sure right now. I have to solve it the first time I am solving. Assuming the axle of the wheel will be frictionless and the force in the rope is 4 Newton, calculate the moment of inertia of the wheel. So now I am going to solve according to this given in the problem, because I made a change most probably. I forgot to change this one from 2 to 25, 2.5. So this acceleration, according to this 2.5 meter per second square, I am going to solve this problem. Okay, so it says that the rope exerts the tension in the rope, and force in the rope is 40 Newton. It's a tension force. And here we have a 4 Newton force. And maybe you remember when we are talking about tension force in 1.3, I said that tension force acts on the rope at both ends. You know, this tension force in the rope pulls this 12 kilogram mass in this direction back, and it also pulls this wheel in this direction and causes it to start rotation. Yani this force, in fact, yani in the rope acts on the tangent, acts tangent to the wheel as 40 Newton, and causes this wheel to accelerate. And I know that linear acceleration of this object mass is given in the question as 2.5. It is at the same time tangential acceleration of this point on the wheel, because wheel is attached to this mass. A mass is accelerating with 2.5, which means this point also must accelerate with the same linear acceleration, which is called in rotational motion tangential acceleration. And this point, yani the rim of the disk will have a tangential acceleration which is equal to 2.5 meter per second squared. Why we need this? Because I need alpha to calculate moment inertia. Because moment inertia is equal to, I know that torque is equal to I times alpha. I will calculate torque, but I have to calculate first how much is the torque. Then I have to calculate how much is alpha. Then I can calculate I. So torque I can calculate because force is tension force causes the torque. So from force to the extra rotation, I know the distance is the radius of the wheel. And it is given in the question as 10 centimeter and 0.1 meter. I can calculate moment of inertia. I can calculate torque, then I can calculate alpha, then I can calculate I. So let's start calculating first alpha because I know that tangential acceleration on the surface of the disk is R of the radius of the wheel multiplied by alpha. Tangential acceleration 2.5. R is 0.1, yani 10 centimeter, multiplied by alpha. So alpha is going to be 25 radian per second square. We got alpha. So after that, I need to know what is the torque. It's very easy because torque is equal to Ft sine theta. I know that. Ft sine theta. F is the tension, which is 40. Distance is radius of the wheel, which is given 0.1. Angle is, because it is tangent, this rod is tangent to the wheel surface. So sine 90, this angle is 90, sine 90 is 1. No need to write it. Torque is going to be 0.4. Pardon, it's not 0.4, it's 4. Sorry. Torque is 4 times 0.1, it is 4. Not 40 times 0.1, which is 4. So torque is 4 divided by 2.25. 4 divided by 25.
It's 0.16.
Yani B is the correct answer. Without any external torque, it is possible for an ice skater to change. Moment of inertia of his body. Moment inertia external torque ile alakalı değil. Moment inertia depends on only the shape, mass, and extra rotation. So you can change it without applying a torque by making the change in the mass, by making change in the shape, by making change extra rotation. So without any external, it is possible for an to change moment inertia. Correct. This is correct. If you change moment inertia, according to conservation of angular momentum, because if no external torque, which means angular momentum is conserved, if you make a change in moment of inertia, which can increase or decrease, angular speed also increase or decrease. So this is also possible. Angular momentum of his body impossible because angular momentum only changes by external torque. Question says without external torque, angular momentum is conserved, and it cannot change. So in this case, A and B, correct answer, yani D is the correct answer. Then 35. A 0.02 meters diameter coin rolls up 37 degrees inclined plane. The coin starts with an angular speed of 85 radian per second and rolls in a straight line without slipping. How much vertical distance does it gain before it stops rolling? This is a chapter 2 question. It is opposite of releasing an object from the top of an incline and finding the linear speed translation in the bottom. This time from the bottom, we are going to send this coin with some tangential speed, translational speed. How much vertical distance it gains? We will find this. But in the question, angular speed is given. Angular speed is 85, but it doesn't matter because for a rolling object, we can easily calculate linear speed if the radius is given. Yes, diameter is given, but radius we can find. The diameter is half of the diameter is radius. So radius is going to be 0.01 meter, half of the diameter. So I can calculate translational speed. Vt is going to be r times omega. R is 0.01. Omega is 85. When we multiply, we will get the result, I think, 0.85.
Yes.
Vt is 0.85 meter per second. The rest is we are going to use the Heck rule for Vt is equal to root of 2gh divided by c plus 1. But this time we are going to apply opposite case. We will find h. So we have to first remove this root by squaring the equation. So it's going to be Vt squared is equal to 2gh divided by c plus 1. Then let's write h alone, which means cross product. H is going to be, first you should cross product Vt squared and c plus 1. Vt squared times c plus 1. C plus 1 divided by 2g. After that, you will insert the numbers. Vt is, we calculated 0.85, but we should square it. C is, it is a coin is a disk. C is 1 over 2 yani 0.5 plus 1 divided by 2g, 2 times 9.81. I think in the choice, some choice in here, choices are given wrong, I think. But calculated how much? 0.85 squared in bracket 1 multiplied by 1.5 divided by 2 times 9.81. It is 0.055. 0.055 meter, but choices are given in centimeter. If you multiply this by 100, we will get results 5.5. I think I sent this to you to change 5.5 in your group. So, and question number 36. Let's continue with 36. Look identical and have the same moment of same mass, sorry. One of them is hollow, the other one is solid. Which one will win the race when rolled down the incline? Again, we will use the same Heck equation we studied, because at the bottom of the incline, which one has greater Vt? It will win, of course, greater speed, faster. And 2gh divided by c plus 1. They are released from same height. And then, of course, smaller c in the denominator causes a greater v. According to the Heck equation, which is equal to 2gh divided by c plus 1. If we want Vt and translational speed to be greater, c must be smaller. So which shape has smaller c? It is hollow sphere or solid sphere? Of course, solid sphere has a smaller c, then solid sphere will win the race. It will move faster. Question number 37. At which angle between the force and distance from the axis, the force required to loosen a nut that holds the wheels on a car is equal to twice of its minimum value? But this question is about required torque. Remember, when I was talking about required, I said that there is a friction between the objects and a rotator, an object you want to rotate, and this friction produce a counteracting torque. First, you have to produce a torque which is at least equal to this counteracting torque, then rotation starts. Yeah, and this is about the required torque, and required torque to start the rotation of an object is always a specific value. And in both cases, you should produce equal torques. Yani one case, there are two cases. One of them is with minimum force, you are going to produce, you have to rotate the nut. In the second one, you are going to rotate the same nut by a force which is twice of the minimum value. Yani first case is F minimum. We are going to apply F minimum force. But in second case, force which you are going to apply is going to be twice of this minimum force, and 2 times of F minimum. But in both cases, required torques are equal. Why? Because if you want to rotate the nut, you should apply minimum torque, which is equal to torque produced by the friction. It doesn't change. And we are going to, distance is going to be the same for what? Because we are using the same range, but thetas are different. But I know that to produce a minimum force, to use a minimum force to rotate an object, theta is going to be 90. We did this before. Maybe you remember it. One of the problem. So theta 90 in here. What is this theta? We are in the second case when you apply a force which is twice of the minimum value. So I will write torque for each case. Then I am going to make them equal. For this case, torque is F minimum times distance. D. F minimum times T. But for this case, 2 times of F minimum, çünkü force to rotate the nut, twice of the minimum value, times T, and also there is an angle theta, sine theta. These two torques must be equal, which tells you that this F minimum times T and this F minimum times T will simplify. Then you will continue with mathematics. On the left, 2 times sine theta is left. On the right, it's left 1. Then transfer this 2 to the right side. Sine theta becomes 1 over 2. 1 over 0.5. Which angle has a sine 0.5? 30 degrees. When you check your calculator, you'll see that. And a bowling ball with mass m and radius of r starts from rest at the top of an incline of 3.5 meter high, rolls down the incline. What is the length of the incline? V bulacağız önce. We should find the V first, because if you want to find the length, it's an accelerated motion. In fact, it's asking you how much distance this ball rolls. Length of the incline is the distance which ball rolls. I am going to use the kinematic equation, delta x is equal to 1 over 2 V initial plus V final times delta t. I can use this. Time is given. Initial speed is also given, start from rest. Only final speed must be calculated. Then I am going to use this kinematic equation to find delta x, which is the distance traveled by the rolled by the ball, which is at the same time the length of the incline. And I can calculate V final by using Heck equation, which is 2gh divided by c plus 1. 2gh, 2 times 9.81. Age is given as 3.5. Divided by c plus 1. It's a bowling ball is a solid sphere. Yani its moment inertia is 2 over 5, which is 0.4 plus 1. Then you are going to use your calculator. You will find V final. How much is V final? 2 times 9.81 times 3.5 equal divided by 1.4. Get the root. It's 7. 7 meters per second. Then I can calculate delta x. So 1 over 2. Initial is 0. Final is 7. Times delta t is 1.5. So 7 times 1.5 divided by 2. Yeah, and it's going to be 5.25 meters. Question number 39. Two uniform cylinder of equal radii roll down an incline without slipping. The torque exerted on the first cylinder is twice as much as the torque exerted on the second cylinder. The first cylinder has blah blah mass of the second cylinder. This is opposite of the question which is asked in ministry, and also chapter 3 question. Mass produces the force produces torque. Or think opposite way. Torque produced by the force produced by the mass. If the torque is twice, question says that torque is twice, you can say that this twice torque produced by a force twice. Yani Fg twice. Fg is twice, According to F is equal to m times, this must be twice. Yani double the mass doubles the force. Doubling the force doubles the
Torque.
torque. Yani that's why twice must be. The mass also must be twice. So now last question. 350 kilogram merry-go-round is in the shape of a disc. Horizontal is with a radius of 1 meters set in motion by wrapping a rope around the rim of the disc. Pulling the rope tangentially, how big a force would have to be exerted to bring merry-go-round from rest to an angular speed, this number, in 2 seconds. Yani, to calculate the force, I need to use the definition of the torque. Two definitions of the torque is going to be used. F times T is the how torque is produced, how much torque is produced. Because it's pulled tangentially, sine 90 is 1, I don't write it. This torque causes this disc to accelerate by alpha, I times alpha. And in fact, we are using two definitions of the torque. We studied one of them is 2, 1, the other one is 2, 3. F is the question. Distance is reduced, then F is going to be I times alpha over radius. I can be calculated, it's a disk. Alpha can be calculated because final speed, initial speed, and delta T is given. You can easily find F in here. Zamanımız kalmadı. O yüzden bunu bu şekilde geçiştireceğim. Yapabilirsiniz, yapamazsanız yarın bana sorarsınız. Tamam.